Hello, everyone. Thank you so much for joining us at this very special interview where we are honored to welcome Dr. Aurora. And this interview will be dedicated to our special Earth Day event, which is an international project organized by the Earth Science Matters Foundations. Thank you so much for joining us. Dr. Aurora, could you please introduce yourself?
Thank you, Victoria. So it's an honor and pleasure for me as well to be here on this prestigious day, Earth's Day. And being an Earth scientist, I always feel myself very much excited to do something on this day, either on online mode or offline mode. And none other day can be the best to approach the kids, to approach the people who are really concerned about Mother Earth and Mother Nature as well. So a little bit about myself. I am basically an earth scientist who studied geophysics. It's a branch of earth science. And my specialization is concentrated to few meters below the Earth's surface. So I look and search for the availability of aquifers, groundwater, and what is their extent, how much resource do we have at particular location and at particular place. And in short, it's like I'm a hydrogeophysicist by profession, and I have served many communities like Young Earth Scientist Network and the Society of Petroleum Geophysicist. Then I was also a student chapter member of Society of Exploration Geophysicist. And I am settled in south part of India. It's Hyderabad, and my parent institution is National Geophysical Research Institute, where I have completed my postdoctoral, completed my doctoral study, and I am working here as a scientist in hydrogeophysics domain. Apart from this, I am also associate professor for Academy of Council of Scientific and Innovative Research, AcSIR, where I do teaching for the PhD students, and I also have 3 doctoral students working with me in the same aspects, in the same zone. I have a special love for kids, and that is the reason I always find it exciting to interact with them. And as a part of this, I have been representing institute at various places, and most part of the country as well. I interact with kids who are in their 8th standard, 9th standard, and then they have so much of vibrant ideas and questions about earth, environment, water, earthquakes. So it gives me a little satisfaction being a scientist that, okay, we are able to quench their thirst towards the earth science. And day by day, year by year, I feel good because my network of this school kids as well as the people who are really concerned about the Mother Earth are growing, and I really like interacting with them, and that is the reason I am here with you today.
Thank you so much, Tanvi. Just listening to you really makes me smile. Having people like you who are so motivated and so passionate about sharing the beauties of nature and the beauties of geoscience with other people is exactly what we need, and we are so proud to have you here for our interview and as a member of the Earth Science Matters Foundation. So let us take this special occasion and investigate the amazing world that is right beneath our feet. So let us get into the first part of the interview where we discuss just that, the basics of near surface geology. What is that? What is the vadose zone, and what are some of the processes that occur over there?
Okay, yeah, that is very true, because many people really don't know that we have huge amount of matter which is existing below our feet. And very recently, the theme of UNESCO for the World Water Day was making the invisible visible. It was like which we cannot see, which we really don't even try to approach. So what is that? And in fact, this was a starting point for my research as well. So what is below our feet, where we are standing? Like we do, to start with a very, very layman way of understanding things, we all have watermelons across the world. We all love watermelons. So when we cut a pie out of the watermelon, then we got basically a three-layered structure. The top one is a green zone, and then we have a white zone, and then we have the edible part, which is a red zone with black seeds into that. So this is the way I start with taking it to the layman. Like the green zone is the part of the earth where we are standing. So it is the topmost zone, which we call as the crust. And then the white zone, which we see is below that. It is called the mantle. It is more thick in thickness, and it protrude more. And then the red zone, which covers a major part of the Earth's interior, is called the core. It is further divided into inner core and the outer core. But let's not go into those things. And it is again watery fluid, and from where most of the volcanoes erupt. Now we are standing on the green zone, the green belt, and if we see minutely, then there is a very thin layer of the green belt also, and that is called the vadose zone, basically, which is thin, very thin. At some places it don't exist as well, and it has little bit of moisture in it. It is not completely dry. So when we see, if we see some layer of the earth visually, then top few centimeters or top few meters, say 1 meter or 2 meter, we see that brown zone, which is a soil zone. And then below that, there is some thick rocks or some fractures or some weathered material, which is called the vadose, unsaturated zone or vadose zone. And this zone reaches from top of the soil to the top of the water table. So if this is the water table and this is where we are standing, so this complete zone is called the vadose zone. And it is filled with many things, and there are many processes which are happening there. But it is very much important because this is a zone which helps our aquifers to get the water. So whatever rainfall is happening on the surface, that rainwater enters the water table through this zone. So if there is no vadose zone, there will not be any aquifer present.
Yeah, that's true. And yes. Thank you so much. So let us investigate the vadose zone a little bit further. How is it different across the planet? Because we know there are different types of soil that affect the rate of percolation, or the rate at which water seeps through this vadose zone and reaches the aquifers. So what characteristics can we use to describe the vadose zone?
Yes, actually, if we see that vadose has come from a Latin word which means shallow. So this zone from the point where we are standing and to the water table is filled with many things. And when the movement of water is happening within this zone, then many branches study that movement, especially a domain of soil physics or hydrology, and in particular hydrogeologists. They study this zone because whatever is the moisture or the water present in this zone is being taken for agricultural uses all over the globe. And many flood control studies also found this zone very important to see and to create a zone where excess water can be moved or can be taken up. Apart from this, the contaminant transport models, the contaminant plumes which are happening across the world due to various sort of pollution, they also find space in this zone. So technically, if we see, then this zone is a combination of many forces. We have the adhesion forces working in this zone. Then we have capillary action, capillary forces working in this zone because of the root of the plants and the tree. And if this zone has it, if it envelops the soil, then the water which is retained in this zone is also called the soil moisture, or the moisture which is present on the top few centimeters. It can be filled with fine-grained soils, and the capillary action, it causes the pores of the soils to be completely filled with water above the surface also, and below above the water table as well. The basic principle which works in this zone is the difference of pressure head and the atmospheric pressure. So whenever these pressure tries to balance, or one is more than the other, the movement of the water or the grains or the soil or the moisture happens. So it is a very deep science again, very complicated science again. But one thing we also need to take care now, that the researchers all over the world are studying this vadose zone in combination with atmosphere, or we can say the meteorological sciences, and now it has extended to critical zone science. And well, I don't want to complicate it further, but vadose zone is a part of critical zone, which is below, which starts from the top of the water table and goes till the top of the trees. Means where we are standing, see, so it extends little further on the top.
So that is basically like studying the biosphere from the geologist's perspective, right?
Yes. And why we call it as critical zone? Because this particular zone, like which starts from the top of the tree or the canopy of the tree and to the water table, it is considered as the skin of our Earth's surface. So we can imagine, if we don't have this skin, so what will be the criticality? This is the living portion where life exists, and it itself says how important this is. And then scientifically many process, so it's not a one process.
Sure.
We have to study microbiology, we have to study the atmospheric sciences, then soil sciences, geology, and then again hydrogeology. And we use, as a geophysicist, we use various tools to study and monitor it. So it's an integrated science and very important.
It sounds very interesting. And the way I like to think about it is the critical zone and the vadose zone as well is the place where all sciences, natural sciences, meet together. So you can literally think of biology, molecular biology, microbiology, physics, chemistry, all of that you can use to study and understand it. So my question to you, Dr. Arora, right now is help us understand the perspective of a geologist on studying the vadose zone. Like, what is the daily work of a geoscientist look like?
Yes, see, as a from the geologist perspective, we study basically the near surface of the earth. So and we use various physical principles to study it, or various geophysical methods which are used to investigate either the shallow subsurface, which is only hardly say 10 meters or 50 meters, or like say 200 meters, not much beyond it, and what are the anomalies or small scale features present in this subsurface itself. If we closely say, then we are exploring this near surface by using the geophysical methods, and we can use different geophysical methods like seismic reflection, seismic refraction, and gravity methods, magnetic methods, electrical as well as electromagnetic methods. And in each of these methods, we have several branches, several constraints and limitations, how to use the principle, how to apply the tools, and how to get the data, how to get the features which are present in this vadose zone or the critical zone. And then we as a geophysicist, we interpret these methods and develop the technology to get water exploration, or if some minerals are present, or if we go further down, then if oil exploration can be done. But the best part of using the geophysical tools and methods are that we can use it for variety of application sciences, especially the now the upcoming fields are medical geology, which is applying these tools. Then for military intelligence, criminal investigations, we are using it. Apart from our traditional things like environmental sciences, geotechnical investigations, and sometimes many times the archaeology departments all over the world, they use the geophysical methods and principles to explore the things. And we are also using the tools with the practical applications to study the biogeochemical cycles as well. So we monitor continuously what are the status of contamination or pollution or water table movements, how the water is moving through these zones and reaching to the water table. So a lot of applications are there.
A lot to choose from when it comes to studying near surface geology. Some of the methods that you mentioned for studying the vadose zone sound very daunting at the first glance, like seismic refraction. What is that? Like, and what is it used for? Can you give some examples?
Well, yes, seismic refraction we do use, and it is basically working on the principle of Snell's law. So when we have like Snell's law of refraction, it is being taught in 8th standard or 10th standard. Like when some source, some seismic source is used to send the waves across some medium. So these waves propagate, and I'm not sure whether all the students, when we were in standard 9th, we were also shown that example by our teachers when we dip a pencil in a glass of water. So this is how, when we visualize that half dip pen from the top or from the side of the glass, then it appears different. Sometimes it appears slightly bent, and sometimes it appears slightly straight, or some maybe at an obtuse angle, or sometimes maybe at more than 60 degrees, but it never appears to be straight and connected to that upper part. So this is how we correlate the refraction methods, that the waves are being refracted and reflected both. But when we study for near surface seismic reflection, we have to use some source in the sense we have to make some noise. So when we make some noise, either it can be by a hammer or by some vibrator on the top of the surface. So it gives rise to some waves. Yes, it gives rise to some waves. In short, it is a small experiment to feel an earthquake. Not exactly we are generating those waves, but when we use up some a small source and we generate the waves. So how these waves reach to the target? What is the travel time being taken from reaching one point where source was there to the other point where some creatures are there, some features are there. So that travel time we get in the form of indications of different waves. And then with this travel time calculation, we get the velocity. We also see what type of waves are being generated, whether they are compressional waves or whether they are shear waves. So this is a further rich domain, but in short, we have these refraction traverses or the seismic lines which are being monitored and acquired by the area of geophones. Geophones are nothing but that receivers which notice the coming of the waves and give an indication to the person who is monitoring them. And with this, we can determine there are some standard protocols and some standard values. We can identify whether this wave has crossed a bedrock or it has crossed which type of rock, or whether it has been refracted from the water, it has touched the aquifer. So we can identify the medium, what medium is being present there. So in very simple language, like we send some signals, we get the rays, and then we interpret it in terms of geology. So this is from seismic refraction, but we also use electrical methods, where in electrical methods, we lay down an array of field processor, like we lay down electrodes. They are stainless steel rods, and two electrodes may act as a current source and two act as the potential sources. So when we send the current with a battery injected, we inject a particular amount of current through these two stainless steel electrodes, and then we monitor in which direction that current is moving. Normally it follows the Ohm's law, and then we have hemispherical surfaces through which current lines propagate, and then perpendicular to them are generated the potential lines, which we record at the two other end of the electrodes. So in turn, in this process of electrical methods, when we send the current, we monitor the potential difference across those two layers through which current has passed, and then we interpret it in terms of the resistance, what is being developed, means what was the difficulty found in passage of that current lines, and then with the resistance we further calculate. As a geophysics, we further transform this resistance into resistivity with different calculations of length of the medium through which lines have passed, and depth of the medium through which they have passed, and what it can be, what was the difference between the electrode. So there is a calculation based on that. And finally, the end product is resistivity of the particular material. And the scientists have been working to give some standard values of this resistivity material. Basically, the engineers do that. They do it in the lab with all different type of materials, that what is a standard value. And then we see how close we are. how close the value of resistivity which we have acquired in the field is how close to the standard values. And that's how we see what material can be there. It can be soil, it can be water again, or many times in many places, especially during landslides or some stampedes, then the bones and some archaeological stuff, if some gold is there which is hidden and buried, then we can get an indication there from that. Sometimes nowadays we are using it for urbanization. That means like how to lay the cables where we have a space, the underground cables below the surface, and whether some leakage is happening, or in some mountainous region where is the scope to lay down the tunnels. So these resistivity has a very wide scope if we talk in terms of near surface geophysics.
Look at that, how many different applications of relatively simple physics topics. And for those of you who don't know, Dr. Tanvi also teaches physics and maths at her university. Is that right?
Yeah, I used to teach physics and mathematics to the school students, but in university, I'm basically teaching the geophysics now. So it's more of a physics with application-based science. And of course, mathematics is always involved because we have to deal with waves, equations. So it's the basic crux.
Okay, that was absolutely fascinating. I think it is time to go on and to talk about, Dr. Tanvi, your work. What were some of your personal favorite projects, or some maybe discoveries that you yourself love in this field and would like to share with us?
I'm particularly interested how a particular zone behaves at different seasons while receiving different amount of rainfall, how the output is being driven out of it, and as far as exploitation is concerned. So this time-lapse monitoring of the zone is quite important. So in my thesis itself, I have designed the experiment to monitor my own institute's garden status to see how with time, how a different season, a particular soil is behaving, whether how much moisture it is able to retain with it, and out of it, how much moisture, how much water is able to get recharged to the water table. Because if we don't know how much water we have, we will go on using it. And that's how the world is more and more overexploited nowadays. Because we think that the aquifer or the water which is below the surface is infinite. We think that we can just keep on using it, and we should not be bothered how to put more water or more recharge to it, and we keep on using, so it will be endless. It will never be finished, but that's not the real case. So sometimes what happens, our government institutions or the researchers, they take one-time measurements, and with one time they can prepare the models and they can generate the scenarios. Okay, after 3 months or after 2 years, what will be the situation? Or after 5 years, what will be the situation? And in turn, those predictions, they sometimes fail. They are not 100% correct. So our models are not 100% correct if we have just one point of data. So my interest always excites me to have time-lapse measurements, like in summer, how the soil is behaving. We all know that in summer, the top few centimeters of soil becomes dry. But that's what we see. What about below that? How is going below that? So that we don't see. Okay, so in soil, if we see that in the vadose zone, we have just 50% of moisture. And out of this 50%, hardly 10% is going down due to gravitational pull and other forces. What will happen when there will be rains? So the vadose zone will be 100% saturated. But out of this 100%, again, it's not 100% which is going down. It may be more than 10% for sure, but not everything is being down. But as a layman or as a normal people, we understand, okay, rains are happening, so whole water is going down. So we have enormous water in the aquifer, but that's not the case. It changes with place to place. It varies from geological material, like in desert it may be different, in hard rocks it may be different, what is the lithology, it may be different, but we don't consider that. So and again in winters it will be different, like in frozen countries there are ice, but in country like India, which is always more than 20 degree of temperature, either in south part or in other, we are not ice covered. So what will happen in winters when there is no rainfall? So which moisture will act as the moisture to go down to the recharge, to get recharged to the water table? And the geophysical results always vary in all the domains. If we are considering for near surface, say top 100 meters or 200 meters. So my research interest always includes whatever objective we are taking, either to explore or to monitor the recharge, to see the potential, or even for groundwater management and budgeting. So we should go for time-lapse measurements as per the hydrological cycles. And if not for all 4 seasons or 3 seasons, at least we should monitor it pre-monsoon and post-monsoon season. So what is the situation in dry condition, and then what is the situation after the full saturation of the vadose zone? That will help the modelers to design their models more accurately and more precisely. So this is the first thing, and I always tell my students to monitor the water table regularly. Most of the researchers, I think almost all the hydrologists and hydrogeologists agree with me on that. We do this exercise to monitor regularly, but we forget to get the geophysics data, and this is very important. And also this will help us in the contamination studies. Suppose there is an industry which is polluting and damaging the top few meters. It's a common practice everywhere. We just dump waste in industrial boards also. No matter how strict the laws are, how strict the rules are, as a human being, we try to do these mischievous activities. And this waste out of industries or other things, it damages the water table with time. In India, and I am sure in South Asia, we are facing this problem a lot. So I am also involved in few of these contamination projects where we are monitoring this dumped waste, how far it reached, and then what is the orientation, its extent, and how damaging it can be to the biosphere and to the critical zone as well.
Yeah, I can hardly imagine a field of research that is more important than studying the quality of the water you literally drink every day. So, and it is very sad, the situation with pollution, and that is why we need to study contamination dynamics. Can you briefly tell us what that is, how it can be studied? Because I know that is part of what you do as well.
Yes, contamination dynamics is again an integrated science. How we need to take the data, because it's not a one parameter which is being changed in the near surface on the shallow surface, but it is multidimensional. Like we first thing is which we need to focus upon, like what is the material which is contaminating, and it is extremely difficult to find out. Nowadays, because of this pandemic, so a lot of hue and cry is happening about the waste coming out from the medical field, or waste coming from people, like masks, sanitizers, and even people are not people are trying to find out that we were told to wash our hands like 5 days or 5 times or 6 times in a day. So how much of the sodium and potassium coming from the soaps, it's reaching to the water table or to the vadose zone or to the critical zone. So it's a very minor component, but it is damaging. It's very damaging to the skin. If somebody throws some polluted water on your face or on your hands, then itching starts. Just imagine how the earth starts itching. So it's very damaging. First thing to find out what is the contamination, which is the source of the source of the plume, or say damage happening to the shallow region. And then accordingly, as a geologist, we have to see whether it is more damaging to our surface features like lakes or drains, or it is damaging the biosphere, mostly the plantations, the trees, where it is going, or it is further if we don't have proper treatment plants, sewage treatment plants, or the contamination treatment plants, where waste is being diverted through industry or through other mediums. If some leakage is happening out of it, which is very common, people do ignore this aspect, but which is in fact more damaging than the effluent. So whether it is treated properly, and how the waste are being dumped, how the people are being affected in that area, because it's not only dumping the material in the shallow feature, but how the people which are living, who are dependent on the water or the aquifer of that zone, what type of water they are using it, are they getting it treated? So it's a complete cycle. It's not only that environment or the earth which is damaged, but all human being is being affected. Then our flora and fauna in different aspects, animals, especially street animals who are living on that particular area, birds. So as a geophysics, again, I would say, like, the continuous monitoring with time is really important, because it changes the contamination dynamics of we can call it as plume, or the transmissivity or the transmission of that particular zone. It's changing with time. Sometimes it can be slow, it can become stagnant, or it can spread horizontally or even more vertically downwards. So if we see it with time, how it's happening, with which rate this plume is migrating, then we can at least get alert the near people or the civilization which is occurring there. We can put them on alert that this is a red flag here, or this is the yellow flag zone, or we have the green flag zone which is existing, and a proper treatment plan can be suggested to the authorities, so that this pollution source, whatever source is there, it can be industries or domestic, or even electromagnetic waste, that is again coming up as a very dangerous tool, that waste coming from the dangerous batteries and the lithium goods, that is so difficult to identify. So we can suggest a plan to properly monitor the waste, and then at least a part of the damage can be stopped.
Well, that gives me a lot of hope. And I was wondering, you were talking about offering communities guidelines and maybe even predicting certain processes and how they might affect for example, the rate at which an aquifer is recharged during different seasons. My question is, how old is this study? How much data is there? How much historical data is there for this kind of processes? Because I would imagine the fewer data you have, the harder it is to predict what is going to happen next.
Yes, this is very good question, Victoria, because again, the speed with which data science is happening all over the world. So this data of hydrological sciences is very important. But I must again say, even if we have like 200-year-old data, see, the hydrology and Ohm's law was started somewhere in 1850s by French engineers. You know, they were the first one to see some leakage coming out of a dam site and then how damaging it can be. And then they also did some modeling to save the dam, and it was all manual. It was all with the engineering concept in mid 1850s or something like that. And out of that, it took, like in 1930s, the computer programs were being generated. So that was the first initiative. We could see that the data started taking a shape in black and white. And it was, well, of course, the West is always ahead of East. So more data generation happened in USGS, it's US Geological Survey Department, and then again at some engineering institutions and some universities. Then, in fact, in France, hydrogeologists were very active, and they started modeling as well. So, but it was initially done on in Fortran language, which is almost obsolete nowadays. But that is how the data accumulation started. Still, I must say, if we see the aquifer, it is all over the world. Water is all over the world. So this is small scale of data acquisition or awakening about the science was very less. Resources were available, people were less aware, but still data started accumulation, and the data was being generated and made as a repository. But to be very frank, the data is useful to give some insights, maybe the water table data or in the form of rainfall data or the recharge happening. It's a science, hydrology is the science where we have to take a balance of input and output. So those days data was there, but output was also less. If we use the same data as of now, then it carries no meaning, because output or the usage has developed multifolds. Even if we have it, like 100-year-old data, it will give a trend, but again, the output and the usage has increased maybe 10 times or 100 times than that. So I don't know, at least I cannot foresee that, how researchers can use it. But what we, as of now, we are mostly using the satellite-based data, which is being acquired by different satellites in different zones. And the overall soil moisture data, which is used for groundwater budgeting or different models, is coming from GRACE. That is a gravity recovery experiment, and the satellite from which even students can get the soil moisture data by putting a request. So it's easily available. And many students, many different science, not even the earth science or the biosciences, many people who are experts from computer field or data science or artificial intelligence, they are using this data and giving the predictions in the models. So it's going multifold now. And many satellites are being used, Sentinel, then even in fact, Google Earth is giving very good source. There are some options into it where even common man can see how with the satellite imagery, the lakes or the satellite or the water bodies are being added or closed or diminished, or they have expanded multitask in a multi-direction. So it's a huge availability now.
Yeah, it's a very good thing we have big data science to help monitor all of those changes which are happening at a frightening rate. I sometimes have the feeling that all the changes that are going on are happening with more and more acceleration. But that is why we need young students to go on and to study this field as well. And I was hoping that you, Dr. Tanvi, could offer some inspiration to our audience and as some closing remarks as well.
Well, a message to the young guys and to everybody is like that we are living in Earth and we still have to live. Our generation are yet to come, and the resources which are available to us in any form, they are very much limited. We need to be very cautious and see how we can save it, how we can contribute towards the sustainability of these resources in any form, whether you are a homemaker, whether you are a student, whether you are a professional doctor, or whether you are a laborer, daily wage earner. Then we need to be mindful towards how we are spending this limited resource and how we can be sustainable within limited things as well. If we see the UN, United Nations Sustainable Development Goals, which are for the year 2030 as well as for 2050, then there are almost more than 15 fields in which water is being touched. More than 15, even in education sector, there is a role of water. Even in medical sector, there is a role of water. So this resource is touching every life, and it is coming again from the Mother Earth. So we need to be very much cautious about what we are injecting in the top few centimeters, whether we are having more of plants, more of greenery, or we are having it as a barren land, which is adding nothing to the environment, or how the soil is being saved, a few meters are being saved towards this, and how the water which we are using for our agriculture or other purposes, whether we are really giving it back to the nature in either form. That is a very intriguing question. Like whatever we are taking free of cost or at the expense of what is existing, are we really repaying it back in one form or the other? So this is very, means I always ponder it over, okay, we as an earth scientist or a geologist, we understand this. So we are much more in pain because we know how damaging things are. So this is my only plea to the young generation and to others who are really concerned. It's not the job of an earth scientist or a geologist or a geophysicist. We can just help you guys. We can just help you to know what is the status. But then again, this resource is in your hands. You can do science, you can do socioeconomics, you can do politics, whatever way you want to. But then whatever resources you are using, just think over to repay it back. It's very important.
Yes, and share this information with others. So thank you so much, everybody, for listening. And thank you so much, Dr. Tanvi, for being with us and for having this interview.
Okay. Thank you, Victoria, for having me here. It was really an honor for me to be here with your audience. And thanks to all of them who have been listening to me and keeping the patience. I would welcome the questions or some further inquiries. Maybe Victoria through you, or you can put my details.
Absolutely, we will do that. Thank you, Tanvi.